ridiculous antibiotic for like 6 months. And it was in the cyclic family of penicillin. So I have to be specific. Nothing in the family of penicillin or generic, or it will kill me.
All right, so these oxidation reduction reactions, when you're trying to figure out what's getting oxidized and what's getting reduced, if it's a metal, it's going from a charge of 0. So this is going from a 0 charge to a +2 charge. So it's helpful to write out the half reaction so that you can see. And there are some problems in your textbook that have the anions. They have the nitrate. They have the chloride, the bromide. Eliminate those and just write it without the anions, and it will be a lot easier to identify what's getting oxidized and what's getting reduced. So in this case, you have iron going to iron 2+. And then the other side of the reaction, you have copper 2+ going to copper metal. And this is a charge of 0. Where are my electrons? Where should they be? So is iron gaining or losing electrons? Losing electrons. So it's losing 2 electrons. Now, for this course, it is not essential that you balance the number of electrons. If you just put electrons on the product side of that half reaction, that's all you need, because what we're looking for is, can you identify atoms that are being oxidized and reduced? So as long as you can do that, you can say, okay, well, this guy is getting oxidized. And really, after you've done the hard work of that, you can say, well, I know something else is getting reduced. What could it be? It must be copper 2 is getting reduced. But prove it to yourself. Remember that Rig or Gur reduction is gaining electrons. Gaining electrons is reduction. So make sure that that makes sense. See how this 2+ plus 2- would give you a neutral, give you overall neutral. That does make sense. So copper 2 is gaining 2 electrons. So copper 2 is getting reduced. Questions on that one?
The way I always had to teach myself when I did the same chemistry was, you think electrons have a negative charge, so you automatically think that they're, that they're being kind of reduced or whatever whenever you see like on this side, like that you're having whatever. So I always think it's the reverse.
I see. Yeah, if you think about it in terms of the reactants and the products, and oxidation is losing electrons, so you're going to see those electrons on the products going away, you're giving away those electrons. If you see the electrons on the product side, you're gaining the electrons. So let's go on to the second one, where you have magnesium, so it's going from 0 to +2. You can write out the half reaction. That definitely helps. Mg going to Mg2+. And where do your electrons go? Left or the right? Right. So then we picked it out again. This one's getting oxidized. And in hydrogen, oh good, we came across a diatomic. Metals and diatomic atoms, remember your Hofbrinkels, any of those are 0 charges. So 0 charge. So this is going from H+ to H2, so it's going from a +1 to 0. What has to negate that +1? An electron. You need a negative to cancel out that +1 charge. Now you notice how the number of electrons transferred isn't balanced. In Chem 1, in higher level chemistry courses, you will spend a lot of time balancing oxidation reduction equations. They're called redox equations. And, you know, at first they're not fun, but I really enjoy balance and redox equations. But it's like, you know, a good amount of paperwork to go back and forth with the electrons and all that. We don't require that in this course. All we're looking for is, can you identify what's getting oxidized? Can you identify what's getting reduced? So the fact that these electrons being transferred doesn't balance, doesn't concern me at all. You were able to identify what was getting oxidized, what was getting reduced. And you don't have to worry about copying the two. You can, in your half reaction, if you want to, you can go ahead and do it, and you know that's how you would get it to balance out. But it's not a deal breaker. Spend your time in other places for this exam. Make sure you know what's getting oxidized, getting reduced. You don't have to write out the fancy half reactions. All right, work this one on your own. See if you can come up with this one. So I see a lot of you getting the correct answer. In order for copper with a charge of 2 to get neutral, it must gain 2 electrons. So is that oxidation or reduction? Reduction. Excellent. All right. Then, you know that oxidation and reduction go together like love and marriage, so zinc must be getting oxidized. But prove it to yourself, because sometimes you can get them flipped around. So that's your half reaction. Not that you have to have it, but it shows you that you're losing electrons with zinc. So because you're losing electrons with zinc, that's getting oxidized. So again, the textbook problems, they have a lot of anions that you, when you're asked to identify what's getting oxidized and reduced, they'll have a lot of extra in the equation. Just omit the anions and look at the metals. See how the charges are changing. Questions on this? So, you know, this is something that you will definitely see on the exam. Don't discount it. Definitely study it. Because you will see it. But again, you don't have to spend a tremendous amount of time on it. All right. So the kind of the last part of Unit 2 goes pretty quickly because we're learning more facts and just kind of how they interact.
Why is copper getting reduced?
Okay, back on page 31. Why is copper getting reduced? Copper is getting reduced because it went from +2 to 0. Remember that the charge on the metal or diatomic element that you have, that is 0. Over here you have a +2. In order to get that +2 to equal 0, you need to subtract 2. And that's really adding 2 electrons. Do the homework problems and convince yourself. And there are some practice problems in the pink book too. And you know, we're getting to the late portion of our class. We're just eat or I'm hungry, whatever it may be. You know, you'll get it. Okay. So Unit 2, this second phase of Unit 2 is less problem intensive, more fact intensive. So you'll get a lot of information, but it goes together. So we're going to talk about energy and how there are different types of reactions. You have endothermic and exothermic reactions, how they differ, how they're alike. So an endothermic reaction, energy must be absorbed by the reaction. And I'm going to abbreviate reaction RX. Energy must be absorbed by reaction. What does that mean? Well, there are some chemical reactions where you might have the two chemicals together and they're not going to react. You'll have them sitting together, you'll have them right next to each other, and nothing will happen. No chemical reaction will happen until you put in energy. That's an endothermic reaction. With this type of reaction, the energy of the reactants is lower than the energy of the products. Kind of think of it. You have your energy on the y-axis. I'm kind of getting you ready for these diagrams that we see. So you have your reactants here. And you have your products here. So in order to get this reaction to occur, you have to walk up a hill. You have to put in energy. It's not just going to be an easy reaction to get going. So I have examples of endothermic reactions here. And so the other thing that is required on the reactants is the energy. So we saw this sodium bicarbonate reaction. And now you can, on both of these reactions actually, are they balanced? No. How would you balance the first one? 2 on the right. How would you balance the second one? 2 in front of the sodium bicarbonate. Good. So remember with that sodium bicarbonate reaction that we talked about a while ago, heat was required. That's an example of an endothermic reaction. You have to put in heat in order for this decomposition to occur. Otherwise, it won't happen. If you think about baking soda that you have sitting around, because sodium bicarbonate is baking soda, you think about, it's been sitting around in your cabinet for months, years, refrigerator maybe. So it's not going to decompose. It's not going to make these things unless you heat it. So that's an endothermic reaction. An exothermic reaction, on the other hand, energy is given off.
So that's kind of radiation.
Right, radiation. So energy is given off. In this case, the energy of the reactants is higher than energy of products. So think about this little energy diagram that we have. The reactants are here, and the products are here.
So this is the same thing as physiology. Like the enzyme or something.
Yeah, and we'll talk about that too. So this combustion reaction, methane in the presence of oxygen and a little bit of heat, produces a ton of energy. Think about how we heat our homes. Propane, exothermic reaction. Energy is given off, so we're able to turn up the heat. Depending on what type of fuel you have, it's an exothermic reaction. A wood-burning stove. Combustion reaction, where heat is given off. That brings us to the heat of the reaction, which is the energy difference between reactants and products. So, in this diagram that I have, this is the heat of reaction. This is the heat of reaction. You can't see it. These are a lot of definitions. You will need to know these for the exam. One thing I always suggest is drawing out a little picture. You know, if you're asked a true-false question or a multiple-choice question dealing with this, draw out a picture, label it, and then say, is this saying the right thing or not saying the right thing? Because it's easy to get these words mixed up. They're very similar. Endothermic, exothermic, heat of reaction. How does it all relate? So, and we have more terms on the next page too. So remember, between endothermic and exothermic, which ones need to absorb energy in order to occur? Endothermic. Okay, so they must absorb energy. So that is the one where you have to go up the hill to get to the reactants, or to get the reactants to the products. So you have the reactants here, you have your products here. You have a big hill to go up. This is called an energy diagram. This is energy on the y-axis, and this is the reaction. You can think of it as progress. So when you're close to the origin, you're just at the reactants. When you're further away from the origin, you're getting to products. So an energy diagram for an endothermic reaction looks like this. So there is a point in your reaction where you're kind of halfway between reactants and products. You're not a reactant, you're not a product. That is called the transition state. So this is between reactants and products. All right. Now we talked about on page 32 the heat of reaction. This is the heat of reaction. And then the difference in energy from the transition state to the reactant is called the activation energy. So, you know, some days when you're feeling kind of low or you don't have a lot of energy, you might be lying on the couch watching TV. You can think of the activation energy as the amount of energy required to get you off the couch and to turn off the TV. If you don't have enough energy to get completely up, you're never going to get off the couch. So if you put in, let's say, only this much energy, this reaction will not go. Even though you're providing energy for the reaction, it's not going to go. It's not enough. Kind of like, okay, that's enough energy to get my leg off the couch or my arm off the couch, but it's not my whole body. So the activation energy is the amount of energy that must be absorbed for the reaction to proceed. So the amount of energy that must be absorbed in order for the reaction to proceed. So we just went over endothermic reactions. We did the energy diagram for an endothermic reaction. Now we're going to do one for an exothermic reaction. So an exothermic reaction, what happens? Is energy absorbed or is it given off? Yes. So this releases energy. Okay. So think about this in terms of your hill. Your reactants for an endothermic reaction are higher in energy than your products for an exothermic reaction. So there is still a little hump to get over. And this is where your transition state is. Zoom out. And I'm going to label. I'm going to add an additional definition to your activation energy. This is the difference in energy between transition state and reactants. So even an endothermic reaction has an activation energy. Even an exothermic. I'm going to say exothermic, sorry. TS stands for transition state. So even exothermic reactions have an activation energy. The heat of reaction, they still have a heat of reaction. That's just the difference between an energy between the reactants and the products. So between an endothermic reaction and between an exothermic reaction, which has a larger activation energy? Endothermic has a larger activation energy. It takes more energy to get up that hill. Just takes a little bit of energy to get over that little hill for an exothermic reaction. So endothermic reactions have a larger activation energy. Questions on this? Commit this to memory. Think about drawing your pictures. Draw these two pictures when you get your quiz or your exam. When you're debating about endothermic or exothermic, or what is the definition of heat of reaction. Anytime you're asked something about this, draw a picture, and it will keep you straight.
Mm-hmm. I don't know if this helps anyone, but the way I've had a professor explain this to a class is like if you're driving up a hill, you're having to gas it to floor and maintain the same speed, so you're throwing in a bunch of energy. And then when you're coming down, you're just limiting time.
Right.
It's easier.
There's just like an unknown exoskeletons to keep unknown exothermic reactions straight.
You think endo and exoskeleton?
Like exoskeletons are like ants and skeletons on the outside, and so like at the end of the reaction, energy is outside of it.
Oh, okay.
But like endoskeletons are inside, so you need to take it in.
I gotcha. Yeah, whatever helps you to keep this straight, and very helpful tips. So I like that endo, exoskeleton. Thinking about driving a car, even thinking about walking up these two can help.
There's this one more, it's that KU and Spot Billings that me and my best friend would always take his dog on. And like that hill's where like a lot of the avid runners and Lawrence will like train. And it's like right when you get up to that point around there, even if you're really in shape, you're wet by the time you get up that hill.
Right.
So it's funny to watch cyclists and bikers go up the hill because you see them, and then all of a sudden there's just like dead.
Right.
Soft.
Yeah, I grew up in Virginia, in Lynchburg, Virginia, and it's called the City of Seven Hills. And it is like KU all over. And so it's like being here, it's so strange to walk on. Yeah, it's good to think about. Anything that makes you remember it, is helpful. Okay, so we'll go on and we're going to talk more about chemical reactions. We're going to talk about catalysts. And we'll see these energy diagrams again. The more you see them, the easier they are to understand. So we have two definitions of a catalyst. And you probably heard about catalysts when you took biology courses or your physiology courses, whatever it may be. The first definition I'm going to give you is it speeds up the rate of a chemical reaction. Speeds up the rate of a chemical reaction. The interesting thing is that a catalyst remains unchanged. So let's return to its original state. Catalyst remains unchanged. So catalysts can be reused over and over again. The second definition of a catalyst, and this helps you with those energy diagrams, is it lowers the activation energy of a reaction. All right, so we're going to have E on the y-axis, reaction progress on the x-axis,
Just driving around when it's really windy. It requires more air
You're talking about for catalyst, or you're...
Yeah, like how it lowers the activation.
Oh, I see. Like it's
Because when it's really,
push.
really windy, I feel like you have to almost gas
Mhm.
But if you have a way to take the one down,
Mm-hmm.
like you know, try to put the other down. So
Right.
you're not flowing very much.
All right, let me show you. Okay, so this is uncatalyzed. And then purple is catalyzed. Is this, you can't really see the purple in that, but it's color. Is this an endothermic or exothermic reaction? So look at the reactants and the products. Is it a big hill to go? Do you have to go up or do you go down? Just up and down. So over a little bump and then down, it's exothermic. If you have to go up a huge hill, then it's endothermic. So this is an exothermic reaction. And maybe I'll draw this one as squiggly so you see. Catalyzed. So what has happened here? The solid line is an uncatalyzed reaction. So if you look at the activation energy, it's here. So it's that much activation energy. The catalyzed The catalyzed, look how big the activation energy is. So that's how a catalyst speeds up the rate of the reaction. It makes that hump that you have to get over a lot smaller. What about temperature? You increase the temperature, what do you think happens to the rate of a reaction? What's that?
Faster.
Faster. So as temp is increased, rate increases. And you can think about this with your produce. If you buy vegetables and you just leave them out at room temperature, they're going to start rotting a lot faster than if you put them in the refrigerator, which is a lower temperature, that will slow down the decomposition of these vegetables. So, I think veggies in fridge versus veggies at room temperature. So this decomposes faster, has a faster rate of decomposition. Now, this last example, in terms of rate, might not be as, at the tip of your tongue, but at the concentration, when you increase the concentration of reactants, it increases the rate because there are more molecules or ions to bump into one another, so it's more likely the reaction's going to occur, so more reactions occur. So as concentration increases, rate increases too. So we've learned 3 ways to increase the rate of a chemical reaction. The first is use a catalyst. Second is to increase the temperature. Third is to increase the concentration. All right. So moving on, we're going to talk more about energy. So you probably remember talking about this energy way back when, maybe in a physical sciences course. Potential energy, kinetic energy, and heat. We'll discuss these. Energy is the ability to do work. And so you think of work, oh, I go to work and I type on the computer, but it's actually moving things and changing the location of things. So when you think of potential energy, what type of energy are you talking about? Energy of station, yeah, so energy of position or stored energy. And kinetic energy, I think every child under the age of 5 has kinetic energy all the time, right? This is energy of movement. My children don't have very much potential energy. They have all kinetic energy, but so when you look at this sketch, which the drawing on the left or the drawing on the right, which one has potential energy and which one has kinetic energy? Yes, so the left is all, so this is all potential energy. And on the right, you have the way this is shown. There it's moving, so there's kinetic energy, and there still is potential energy because it's still above the floor. So kinetic energy and potential energy. And I'll draw you this little roller coaster. I'm sure you've seen this before. So when you ride on a roller coaster, and I don't know, if you like riding on a roller coaster, this would be you. If you don't, it would be you. But so you've just gone up this huge hill, and you've done the click, 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 and there's that moment when they stop you. Is that potential energy or kinetic energy? Potential. So you've got all potential energy here. And then you get to going down the hill. And, your eyebrows are up. Oh, you're screaming. Or you might be covering your eyes. I don't know.
Bracing for dear life.
Yeah, just closing your eyes. I had a friend who could never open her eyes on roller coasters. Why go if you can?
Because you get dragged with your friends.
Yeah.
That was my theory.
Definitely, I agree. So you have kinetic energy here, and you have potential energy. So you're moving. Then when you get to the bottom of this hill, and I don't know, depending on whether you like it or not, you're still moving, and so this is all kinetic energy. You don't have the energy of position. You're not above, at the top of the hill. So depending on where you are or what movement you have, you might have a combination of potential energy and kinetic energy, or you might have all potential energy, all kinetic energy. It just depends. Now, heat. This is the measure of kinetic energy of particles. Particles are always moving. They're moving very rapidly. They have a high kinetic energy. Then you're going to have a lot of heat given off. If there's not very much movement, then there won't be much heat given off. Okay, so again, more definitions, but just think about these different drawings. Think about it in terms of that. Definitely a lot of potential for true, false, and multiple choice questions with this portion of Unit 2. Let's try and do one more page. And this is the different properties that solids, liquids, and gases have. So you know this. You just don't know it in terms of a table like this. We all know this. We use it every day. But now I'm asking you to put it into a table and put it into words. So you know it. The shape of a solid. Do solids have shape? Yes. You think of a block of wood, it has a definite shape. So a solid has definite shape. What about the volume of a solid? Does a solid have volume? Yes, it has definite volume. You think about your length, width, height calculation. Yes, you can calculate the volume of a solid. The particle arrangement in a solid is fixed and very close. The particle interaction between solids, between particles in a solid, is very strong. The particle movement in solids is very slow. Now a liquid. Does a liquid have shape? If it's in a container, excellent. So it takes on the shape of a container, or whatever container it is. So shape of container. Does a liquid have volume? Yes. You use your graduated cylinder for it, so definite. Or when you buy your 2 liter of soda product, definitely has volume. The particle arrangement in a liquid is random and close, not very close like a solid. The particle interaction strong. The particle movement is moderate. All right, what about a gas? Does a gas have shape? Shape of the container. What about volume? Volume of the container. Takes on that volume with it. Depending on what type of container you have, dictates the volume of gas that you have. Particle arrangement in a gas is random and far apart. The particle interaction is weak. And the particle movement is very fast. You can think of your friends, think about them in terms of a solid, liquid, or gas. If you have that hyper friend, that would be more like a gas. So we will stop here.